Can you hear me? Yes. So, Assalamu alaikum, everyone. Welcome to the last session of AI Summit. It is the last conference. I hope that you have watched and enjoyed all the previous conferences, and most importantly, that you have learned from it. I'm going to first introduce myself. I am Maria Hajusro, the current co-lead of the code of this season's School of AI. And today we are going to introduce a very interesting topic. Since all of us are familiar with LLMs, and even non-AI people are very familiar with LLMs as a tool to utilize in their daily lives. And the most common thing about LLMs is prompting. So today we are going to introduce the other side of agentic AI, in which we go beyond prompting to build and evaluate agentic systems. This talk will be introduced by the ex-co-lead of School of AI, Narimane Hennouni. She is currently a solutions architect in generative AI at NVIDIA. So yeah, you can go ahead and start, and Narimane, good luck.
Thank you so much. Can you hear me? Just to confirm. Okay, awesome. Thank you so much for the introduction. Again, I'm Narimane Hennouni. I'm solutions architect in applied generative AI. I would love throughout this presentation and this talk today to share some of my learnings and experience from the field. And of course, anything I share here is just my own personal views and opinions. So let's get started with how we can build and evaluate intelligent AI systems. The motivation behind this presentation is that AI is evolving from passive assistance to adaptive intelligence systems. And what we mean by that is that traditional AI systems were largely reactive, meaning that they waited for a user to give a prompt, and then they just generated a response and they stopped there. However, modern AI systems are becoming more agentic. Meaning they are capable of multi-step reasoning, tool orchestration, managing memory, doing planning, and also doing autonomous execution across dynamic workflows. And that's something we need to keep up with, and we cannot just stay with just the reactive foundational traditional models and move towards more proactive approaches. For today's agenda, I'll briefly go through what generative AI is and what are reasoning models, how they are using agentic AI, and an important key part of building these intelligent systems is evaluation. Generative AI, I guess everyone now is familiar with what it is, given the hype around it and the LLMs and the new whatever chatbots, agents, you name it. Everything now is around generative AI. It all started with this transformer architecture, and which we call the iPhone moment of AI, because since then we've seen this bloom. So the transformer architecture was the breakthrough that unlocked this modern state of AI. And unlike previous models, transformers could efficiently process parallel massive amounts of data and learn contextual relationships across these entire sequences. And it enabled the rise of large language models, LLMs like GPT, and making them more capable, accessible, and general purpose as well. So it created this foundation of modern models, and it goes like from LLMs to diffusion models for image generation, etc. And they enable the systems to generate language, images, videos, audio, etc. So it's multimodal as well. Put in simple terms, these traditional LLMs, they optimize for text prediction, meaning they just predict the next token, and then they give you the final output. But they don't necessarily optimize for whether the response is correct. They don't reason, they don't think about what they said, they don't think about what they outputted, they don't have a plan and execute or reiterate on that. And one of the ways that we usually try and improve the output of these traditional LLMs is by doing prompt engineering, meaning we try to optimize a prompt, make it better, so that the response would be better. However, prompt engineering alone cannot fully solve these limitations, which motivated the development of reasoning models, which are models that are capable of reasoning, tool-augmented systems, meaning that the model no longer operates by itself and just generates text, but it can use external tools, external knowledge databases. It has external help in order to produce more accurate answer. It uses retrieval systems using RAG, retrieval augmented generation. So we will be connecting these LLMs to a database so that it can retrieve factual domain-specific knowledge and eventually build these AI agents, which are an end-to-end autonomous approach. Before we dive deeper into what reasoning models are and how these agentic systems are built, one thing I wanted to mention is the scaling laws for LLMs. So scaling laws basically describe how AI model performance improves as we increase the model size, the data, the compute, and the training times. And there were two major phases for how AI systems scale. There was like the pre-training scaling and the post-training scaling. So for pre-training scaling, what pre-training means is, so pre-training is the phase where the model learns the general knowledge. And we do that by feeding it massive amounts of data. And this is the traditional model scaling that drove the rise of ChatGPT or Claude or Llama models. It's basically you're training these models on a huge amount of data to learn general knowledge. And once this pre-training step is done, we have foundational models. So the key idea is that the more data these models have, with the more compute, they become more capable in predictable ways. So they develop general capabilities, multilingual understanding, etc. Post-training happens after the base model is trained. So instead of just making the model bigger, we will try to improve the behavior of the model, its reasoning, its alignment, how it's performing according to a specific task or specific use case or specific domain, and its agentic capabilities. And this usually can be done using SFT, like supervised fine-tuning, RLHF, reinforcement learning from human feedback. We're basically teaching the model how to think, behave, and reason and interact effectively. Recently, in more recent times, a major trend appeared, which is that scaling is no longer happening just during training. We don't have just the pre-training scaling, the post-training scaling, but we also have scaling at inference time, which we call test time scaling. So inference time scaling or test time scaling is the idea that models can become smarter, not just by training the bigger models, but also by spending more compute while generating the answer. Meaning like that instead of producing an answer immediately, the model will reason step by step, explore multiple solutions, reflects on its own output, use the different tools, verifies the results, and it does a lot of iterations before responding. So more inference compute means better reasoning quality. I've been mentioning reasoning a lot, and the reason for that is that this reasoning is the key to agentic AI. So traditional language models, as we've seen, are excellent at predicting the next token. And they do this based on learned patterns that they've seen in the data while being trained. However, these reasoning models go a step further. They allocate additional their additional resources to break down the problems, evaluate the intermediate steps, and improve the answer quality. So basically, a reasoning model is different than an LLM because it does not just generate the answer. It splits the problem into sub-problems so that it can tackle each separately and efficiently. It verifies its response several times, which leads to the final answer being more accurate after detailed thinking. And why do we care about reasoning? Why is reasoning important? So when we use, or the model uses reasoning, we are able to better explain the complex problems, because we can see the whole thinking process. We see why the model did certain things. Why did it make that tool call? Why did it decide to have this output and not other output? We can see the whole trajectory, in which we call trace. I'll go through that later in slides. We'll also have better performance, because the model does think and iterate and reflect on its own answers, and thus comes with increased explainability, as I mentioned, by checking the traces of the model. And also the scale, the LLM test time performance does scale, because we're using more test time compute to have better reasoning. And these reasoning models have helped the agent with contextual understanding, because it provides the agent with more context. It combines multiple resources if you're using different tools, or if you're using retrieval augmented generation. It also helps with the answer validation and the handling of ambiguity. If the model is not sure about its response, if the prompt is not clear, it can reflect on that and make sure that the answer is valid, or try to get better understanding using external resources. In a nutshell, if we're comparing traditional models versus reasoning models, the traditional models generate direct answers. However, the reasoning models plan step by step. The traditional models use implicit reasoning, and it's hard to verify their answers. However, for the reasoning models, we use explicit reasoning, because you can see the step by step they go through, and which makes their answers more interpretable. Traditional models usually just do a single pass generation, which also makes it weaker, which also make them weaker on longer tasks, because usually longer tasks are a sequence of smaller problems, so they don't have that intuition to dividing a bigger problem into smaller problems. So they usually struggle with that. However, reasoning models, they reflect and correct themselves, and they do better with multi-step reasoning. Let's try to see how these reasoning models are built. The chart may be a bit overwhelming, but we go through it like step by step, not in great details, but just to give you an idea of how usually these reasoning models are built. Starting from the left, we have the pre-training stage, which I already mentioned. So everything starts there. All models, all LLMs start with the pre-training. This is an important step because it helps the model learn general patterns, learn language, code, word knowledge, etc., from massive amounts of data. And usually we get this data from the web, from books, code repositories, etc. So at this stage, the model is a powerful statistical learner, but it's still not optimized for reasoning or human interaction. The next step is post-training. In this step, we teach the model how to interact, how to better think about specific use cases, and how to interact with humans. So this includes, we can do like supervised fine-tuning and reinforcement learning from human feedback. So for the fine-tuning step, like we have supervised fine-tuning, for instance, for reasoning, this is where reasoning-specific capabilities start emerging. So the model is trained on higher quality reasoning data and does step-by-step problem solving, logical decomposition, be it math, planning, etc. At this step, we're trying to increase the agentic skills through supervised fine-tuning. Then we have the reinforcement learning step. For this one, we try to make the model more aligned. We usually use this RLHF and alignment terms together because we use reinforcement learning to make sure the model is aligned. And what we mean by aligned is that it does good on instruction following. So if you give it specific instructions, make sure it follows that instructions. And most of the time, this is something we do evaluate for, because it's important that the model sticks to what it has been instructed to do. We make sure that it meets the user expectations, that it's safe. So instead of just learning by examples, which happens in supervised fine-tuning, the model will be learning through feedback signals. And we usually also have a human in the loop component here. So we'll have a human, a real person, evaluate the responses, give some signals, give some feedback, etc. Then we do have safety and robustness, which is a very important component, because we don't just care about the accuracy of the model, but we also care about the quality, the safety, and the efficiency. And this is why we do the whole evaluation step after that. And we have different approaches of how we can evaluate the models. We have LLM as a judge evaluation. I'll talk a bit about it later on. We have evaluation specific to agentic systems. We do benchmarking. We can do also human evaluations. And finally, we have the deployment stage where the model is deployed in the real world. And when the model is deployed in the real world, it is continuously interacting with users. And then we can have also more feedback. So all of this creates a feedback loop where even at the end, once it's deployed, it does not end there. We keep getting feedback from the users and different applications, etc. And we feed that feedback so that we create what we call this feedback loop to improve the models. And another important thing to notice is that different stages requires different sources, types of data. Usually pre-training relies heavily on broad internet scale data. But reasoning and alignment usually need more curated data. This data can be reasoning traces, human feedback, safety-focused data sets. So the data that goes into these stages needs to be curated carefully. So this is overall the whole workflow of how we build these reasoning models. And another important thing is for the evaluation part here on the bottom is that we don't evaluate just for accuracy, but for these model reasoning systems, we also care about, again, safety, robustness, efficiency, and the agentic behavior in general. Now going deeper into how we use this reasoning model in agents. But before talking specifically about agents, we need to, whenever we have a problem or use case, we need to choose the right level of intelligence. Not everything needs an agent. Sometimes we try and go with the hype. The same thing, not everything needs AI. Sometimes we just try to go with the hype and overcomplicate things or provide complex solutions to really simple problems, and that just makes our lives harder and create even more problems. So when we are building applications with LLMs, it's usually best to find the simplest solution possible and only increase the complexity if needed. Meaning that sometimes you may not even need to build an agentic system at all, because because even these agentic systems, they often trade latency and cost for better performance tasks. True, you may have better output, but you also given in more time and money for that, and you should consider when this trade-off makes sense. And then when you need more complexity, or if you don't need that much complexity, sometimes workflows offer better predictability and consistency for well-defined tasks. So what's the difference between an agent and a workflow? Agents are systems where LLMs dynamically direct their own processes and tool usage to maintain control over how they accomplish certain tasks. So they are autonomous. They have the full control over what to do in order to get to the goal. Workflows, on the other hand, are systems where LLMs and tools are orchestrated through predefined code paths. So it's predefined for them. They just operate following that path. So that's why it matters here. It's about choosing what do you really need for your problem or system. A fun joke aside, it's like usually sometimes a Python script is the best AI agent you can use. So we need to carefully think about that. And usually agents work well when the task has clear success criteria, meaning it has a defined goal. We know how to fail and recover from that because it's an iterative process, like building agents and fine-tuning them for a specific case and making them specialized. That's another thing, is that having general agents is usually a bad idea. You can want to have an agent specialized in a specific task. For instance, just building summaries of research work. That's it. You don't want to have an agent that will do the whole system for you, that the agent will do the summary, will read whatever you have, do the summary, generate the output, create the slides, send the report, everything done by one agent. So when they are general, they are usually performing worse. It's also important to have verification that is cheap and fast, because we will be doing that a lot. We don't want to waste a lot of time waiting for it and spend a lot of money on that. So the verification needs to be cheap and fast, and we have always human in the loop, because as much as these agents and these systems are autonomous, it still needs human supervision. We cannot just let it operate by itself. And that's how it goes with the verification and detection of failures, and then implementing this whole feedback loop. On the other hand, they fail when the success is very subjective. We don't have a clear definition of what success means, so the agent would be going all in the round. Failures are expensive, so we cannot keep doing the failure analysis and integrating the feedback, because it's going to cost us a lot. Or even when the verification is slow and ambiguous, because then we cannot integrate these learning fast. And if it's ambiguous, we don't even know what to integrate. And they are also, if they are designed to operate without oversight, that's a recipe for disaster. For going to specifically what agentic AI is, it's basically the humanity's ideal of artificial intelligence. So it's like the perfect world of where artificial intelligence shines. Is like these agents are able to achieve complex goals with minimum human intervention. You just give it a task. You make sure you have your agent is well suited for that task, and it will do everything for you. Maybe from time to time you just want to check how it's doing, and yeah, you no longer have to do any work. So that's what you usually think about how agentic AI is. So basically an agent is this system that interacts with the environment, does the planning, use tools, and make decisions to adapt to the changes in the environment following its actions. We have different types of agents. We have coding agents, browser agents, research assistants, customer support agents. And what you can see here is that they are all specialized. Again, if you want to have a good agent and with a good output, make sure that it's specialized for specific tasks. So they do extend LLMs by having the ability to take actions. They have a memory so that they remember what they've done. They store information and feedback and learnings for future iterations. They have the ability to plan, meaning that before taking an action or before giving any output, they do plan their actions, and then they take the actions, and they do interact with the environment. So they interact with their environment, they receive feedback, they change their actions and plan it accordingly. And so they have the powerful ability to reflect, to plan, to use tools. So we have different types of tools. We can have, like, for instance, search tools, external calculators, APIs, code interpreter, you name it. You can the internet has millions of tools. You can create your own custom one if you're working on a specific domain. It's usually best to start with something that has been tested before and is already available. But if you think that your use case or your problem is very specific and no such thing exists, you can always build your own tools. So these tools do extend the capabilities of the AI systems beyond just pure text generation. And so these modern agents can interact through the tools with search engines, APIs, databases, browsers, even like other shell environments, and of course other agents, but other agents are not a tool in this case. We're just talking in general about the tools. And all of this to help craft a response that is more specific and more curated. If we see here, this is an example of a research assistant agent. Well, we have a user give a prompt to our research assistant agent. This assistant agent is powered by tools and memory. So for the memory, it's basically, so when it comes to agentic memory, there are two types of memories. Memory where us as users will be adding links or data that we think is needed for this agent to perform its job best. For instance, you can connect it to, you can put links or documents on specific domain knowledge that you have, or like some specific instructions that the agent needs that the agent needs when it's doing the planning and reflection. So basically, when you're interacting with the agent at each session, it will be loading this memory, understanding what it has so that it can better perform. The second type of memory is the memory that the agent itself populates. If you are interacting with an agent and you see, for instance, that it's performing bad on a certain task, you can give it feedback. The agent will create a document for that feedback or for future iterations so that next time it knows what or what not to do. And then we have the tools. For the tools, as I just explained, we have a variety of tools. But for instance, for the research assistant agent, let's say we need a web search, because usually if we have some research topics, we're going to be searching the web for research papers or existing code bases that may implement part or the research project we're working on. Another important thing is that we can integrate RAG. So RAG can be used as a tool. RAG is retrieval augmented generation. And in this case, we call it agentic RAG. So the agent will not just receive the retrieved documents passively. So if you have created data specific to your use case or domain specific to whatever you're working on, the agent can decide when to retrieve, what to retrieve, whether the retrieved contexts are sufficient, or it needs to use another tool like the web search to get more information, or it needs to refine the research. It can even change the prompt that will be later embedded for the vector search, etc. So by also using RAG, we are improving the factual grounding because we are retrieving this external information that the agent needs. And then we go again through the agentic workflow. So we'll have the planning, the retrieval. If we were using our RAG systems, we read whatever we retrieved and whatever we got from the tools. It gets synthesized and then delivered to the user in the final output. However, using tools do introduce new problems because it can do incorrect API calls. Sometimes it doesn't use the right tool, or it knows which tool to use, but it does a wrong API call. If one thing fails, it causes cascading failures, meaning that failure just cascade to the other sub actions or sub problems. There's a security risk because we are connecting with and interacting with the external world. So we may be exposing our data, we may be sending data that should not be on the on the internet, etc. There are some permission management and reliability concerns, because again, we are interacting with the external world. So if we're bringing in stuff that should not be brought, or we are making calls that should not be made. So this is something that we need to make sure the agent is doing properly. However, trying to evaluate this system and making sure that it's working properly end to end can be difficult. And it's harder than evaluating the traditional large language model systems, because even for the same task, and even if it's the same output for two agents, we can have different reasoning paths. An agent could take 2 tool calls to give you a certain response, and the other would take 5 or 6 and give extra steps or extra reasoning, or think 3 times about its response before generating the same answer. So that makes it less predictable, less deterministic, which makes it harder to evaluate. So therefore, building these reliable AI agents is not just becoming a modeling problem. It's not just about an approach on how you can model the knowledge and just let the agent do that, but it also comes back to a system problem, because it's the whole system interacting with each other. We have an infrastructure problem because of how we're deploying it, how it's running. Is it all local? Are you doing hybrid? Where are the tools? Where is the model hosted, etc.? An evaluation problem, because definitely need to make sure our agent is working properly, reliably, efficiently, and also a safety problem for the reasons I mentioned before. So what we usually do try to measure when we have agentic systems, we measure for accuracy. Are the answer correct? Compliance. Reasoning. Is the reasoning logical, consistent? And we do this by checking the traces of our agent. Tool use, did it use the right tools? Did it use more tools than it should? Because at a certain time when you're trying to optimize for latency and cost, true, an agent may use 5 tools and give me an answer, but could that be reduced to maybe just 2 tools, where only 2 tools really necessary to get the answer, and not use 5? Because using 5 will mean like 5 API calls. So, and each API call has its own cost, has its own latency, because the agent have to wait more to get the response, etc. Reliability, meaning is the agent consistent with its responses? If I give it the same, this is for one agent, if I give it the same prompt 2 or 3 times, it's able to provide consistent answers, or is it going to contradict with itself? Does it produce any harmful output? Safety is a big concern when it comes to dealing with AI agents. And is it being efficient, again, because of the latency and cost? And usually we try to do this agentic evaluation on 2 axes. We have what we call objective evaluation and subjective evaluation. Objective evaluation is something that we can just do using conditions, or like what we call code evaluation, meaning that an example would be, for code evaluation, if the score is equal to or less or equal to, or if the number of the mentioned locations in a certain research paper is equal or less to. So you can define just by using conditions or by using code in general. It can be also like unit tests or functions. It can be easy. Wouldn't say easy, but I would say more predictable. Subjective evaluation is when we don't know exactly, and we need, as if like you have a human being and it's trying to give you subjective opinion on a certain thing, because there is no wrong or right, or there's no one way to do things. And the other axis is, do we have ground truth data for that, or we don't have ground truth data for that? By ground truth data, meaning what we mean by ground truth data is that for a specific sample, we know what the answer should be. So if you try an example of doing an objective evaluation, and we have the ground truth data is was the code generation evaluated using unit test. So for that, the objective evaluation is through unit test, and we have the ground truth data because we know what the output should be. If we're doing subjective evaluation with ground truth data, is an example is summarization quality compared to a reference summary. So the subjective evaluation is how is this, what is the quality of this summarization, and we usually either need a human or an LLM to judge the quality, and then we have a reference summary that we compare these two summaries against each other, and we can know what is the quality of the generated one. If we don't have ground truth data and we're trying to do objective evaluation, an example of that would be the latency or tool success rate. If we take a latency example, is that for a specific agent, we can measure its latency, but we don't necessarily know what that latency should be. That's why we don't have a specific ground truth data for that. If we want to make it more constrained, we can say that the latency should be under a certain number of seconds, certain time. That's what the latency will be. If we were trying to do like subjective evaluation without ground truth data, an example of that would be how helpful this agent is. We're doing subjective evaluation. We need a human or an LLM as a judge to rate the helpfulness, how helpful the LLM is. It can be a score, but we don't know exactly what the ground truth is, what should the helpfulness will be. We just want to evaluate it and get a sense, a quantitative metric of the helpfulness. I mentioned quite a few times LLM as a judge, which plays a big role in the subjective evaluation. So what is LLM as a judge? It's basically when we're trying to use another LLM to evaluate the quality of our LLM's output. It's the same as you have a human judge judging the output, judging the quality, etc. But we cannot always afford to have humans being used because it costs more in terms of money, in terms of time. And when we want something faster and approximate, because indeed humans will most likely be more accurate than LLMs, especially in specific fields. And sometimes in those specific fields, actually, it's better to just go with humans regardless of the cost, like medical fields, legal, or safety critical systems. But even when we're using LLM as a judge, it doesn't mean that we remove the human component completely. Human review is definitely always still important. And usually we have two types of LLM as a judge evaluations. We have single answer scoring, or we have pairwise comparison. For the single answer scoring, I'm sorry, we don't have to. We have three. Sorry. So we either have single answer scoring, where we try and given a certain answer, it gives it a specific score. If, for instance, we do the latency or the helpfulness, this is the output. How helpful is the output? Or we do a pairwise comparison. For pairwise comparison, we give it two model outputs. Let's say we're trying to compare two models. So we have our third model as a judge, and we give it the output of the two models, and we try to compare them, which one is better. And the third approach, which is usually the recommended approach, is having a rubric-based evaluation, meaning that we have explicit criteria, and we try to evaluate that output on different criteria, so that we are not just biased towards one thing, and the judge has more room to explain why it thinks that this is better, or this score should be attributed to this response. People use this LLM as a judge, again, because human evaluation is expensive. Usually the traditional NLP metrics are weak when it comes to generative AI. as these AI systems are evolving and becoming more autonomous, the traditional metrics don't capture all the nuances and what really needs to be evaluated for. We usually need a faster iteration during development because sometimes human evaluation can be slow. And it's useful for RAG systems, agents, chatbots, coding assistants, etc. Most of the agentic workflows. However, before moving to the next slide, I want to give an example of what a prompt for your LLM judge may look like. You start first by giving it a persona, like the context. So you say you are an expert evaluator, and you give it a rubric or the explicit criteria that you want your LLM as a judge to score against. So here we ask me to evaluate for correctness, completeness, and clarity. A step further would be to, for each of these criteria, explain what does it mean. Because sometimes clarity can mean different things to different people, and it does the same for different LLMs or for the LLM itself. So if you really want something specific, it's helpful to also add what that explicit metric mean. And usually tell it, or give me a score between 1 to 5, 1 to 10. And it's important to ask it to explain why, because you want to understand the reasoning behind this score so that you can see if your LLM is really being compliant and is really doing what you're asking it for, it's hallucinating, or it's going another route that it may give you a clarity score of 9, but if you don't know why, or if it's doing it for the wrong reasons, you want to catch that. And we can see here, like the example, usually it's a JSON format, giving scores for each of the explicit metrics and also the reasoning behind it. So, however, these the use of LLM as a judge come with specific with some limitations. We have the first one is the bias. These LLMs can be biased because they usually prefer verbose answers. So usually if the answer is longer, they tend to give it a better score. They usually favor outputs similar to their own style. So that's why one rule of thumb, you never use the same model to judge your model. For instance, if you using, let's say, Claude Opus 4.7 as your model, you're not gonna use Claude Opus for 4.7 to evaluate, to judge the model, because it's gonna be biased and it's gonna favor the responses of your of like the model of the same kind or the same family. It also, the LLM as a judge may have some inconsistencies. So the scores can vary across different runs, different prompts. Even if it's like for the same model that you're evaluated against, if you run it multiple times, or if you use different prompting, it may have different results, which makes it inconsistent. It can hallucinate or make mistakes at the end. It's still another large language model, so this is something it can fail at. It can be sensitive to a prompt, so change of prompt changes the score, changes the output. So just, it's important to know that it is a very helpful tool for evaluation and for iterating faster on these systems, but it's, again, it's not perfect, and it's not a replacement for humans. Another important thing that we need to do with our agentic systems is error analysis. And what we mean by error analysis is trying to see where our agents fail. Sometimes we take the whole end-to-end pipeline and there's something wrong with it, but we don't really know what is wrong. That's why we need to take it component by component and see, for instance, if we are at the LLM, the first LLM box, and we have, it's using a web search tool. So did the LLM provide the wrong prompt to web search tool? Did the web search tool return the wrong response? Did the LLM fetch the wrong resources? the wrong sources? Did it use the wrong tool in the first place? Did it make an error when doing the summary or synthesizing the whole process? And this is what we do when we look at the trace. I mentioned trace before, but basically trace is taking the end-to-end thinking and step-by-step process that our agent went through, from the user prompt to what it thought, what prompts it generated, what tool it used, etc., and going through them manually. And usually we do that for like a sample of like 10 for 10 or 20 samples. Usually we pick those samples to be representative of different use cases, and then we go through them manually, check the output and every step, and then we attribute a score to each of the steps and see where is it failing the most, because we want to tackle this as a component per component issue. We cannot just say, oh, the whole system is wrong and you then can nothing to do about it, or like you don't know where to fix it or how to fix it. So the same way that the agents do divide the problems into sub-problems, we also, when we are evaluating and analyzing these systems, we take them component by component. And a span is the output of one step. So the trace is like the end-to-end thing, and then the span is the output of a single step. So usually check them span by span, which are all included in our trace. And usually how we go about it is you need to develop this intuition or a habit of looking at traces. This is something usually neglected, so I'm trying to emphasize on this. And we need to develop the habit of looking at these traces, analyzing it, although it may be tiring or manual. Or you can even just take the traces and give it to another model for it to judge if you don't want to go through the whole manual process. But still, you can investigate the output of the second model. It helps you maybe give you a summary, or it may detect a certain pattern across different samples. But it's important to do this error analysis. And you also have to be careful about that, because once you do the error analysis and you're gonna be on the evaluation again, the end-to-end evaluation is expensive. So you gotta make sure you want first to make sure that component is performing as you want, is performing towards a specific criteria or metric that you set, and then integrate it back into the whole system and do the end-to-end evaluation. So that's why we tackle it component by component. And some small maybe improvement suggestions on how you can do improve the performance of these different components. So if it's a non-LLM component, let's say you have a rack system or a tool, whatever, what you can do is that you can tune the hyperparameters. Let's say you're using a rack system, you can tune or tweak how many chunks it retrieves. Instead of 5, you can have 10, you can have 3. If you're using a web search, you can tweak the verbosity, how many results it returns, or you can even just replace the whole component with another component, may do better. If we're talking about the LLM itself, we can try doing some prompt tuning. Changing the prompt may result in better outputs, better responses, and then it can use better tools or more appropriate tool per se. You can try different models, because nowadays, like models, each model is better at certain things. Some models are better at code. Some models are better at let's say, understanding a certain language. Or you can even, if you have the resources and you want to investigate, you can even fine-tune that specific model. But and here it comes, like, especially for trying different models, we need to develop this intuition for model intelligence, meaning that we know that different models are good at different tasks. And the way we do that is that by playing with different models, by experimentations, you can read other people's prompts, like which prompts are people using for specific models, so that you can know usually which model to use for which case. And the last thing I want to mention about the agentic evaluation, I've talked a lot about having a good output, although it is important and it's the most important, I wouldn't say, okay, let me rephrase that. It is important and it's a very important thing to evaluate for. It's not enough to just have a good output. Or if you build your end-to-end system, it produces good output as you want, and you deploy it, and then millions of users start using it. But for each user, you're making 5 to 10 API calls, 5 to 10 LLM calls, and everything is costing you a lot of money and a lot of time. Multiply that by like million, and it's gonna be super expensive, and it can cause a lot of bottlenecks, system saturation, etc. So we need to also care about the cost and latency. So you want to, if we go back here to this one, you want to know the cost and latency of your end-to-end system. So every step of your end-to-end system. So for every step of the pipeline, it has certain latency. Usually for LLMs, the cost is per token, and for the tools, because we make an API call, so it's usually the cost by API call. So we want to have the cost of each step, the end-to-end cost, and the end-to-end latency, and try to improve for that. And some ways you can improve for that is that use parallelism. So if there are like any things that can be parallelized, make sure you take advantage of that. You can swap models by smaller or faster models. If you care about latency, try and use a faster model, or for the cost, it will be less expensive to use a smaller model. Because again, we want to have the simplest solutions for the problem. Sometimes why you don't need 120 B model for task or for something that can be done with like 1B model. So again, choose the simplest thing that does the job, and also try different providers. Like different providers have different latency and cost rates. So what's next? For the world of agents, we can see that agents are definitely already actually being multimodal, supporting multiple modalities, and which help with the embedded AI and robotics as well. So they're making their way towards the physical AI world. These are becoming self-improving systems with their reflection and planning capabilities, and the autonomous workflows are emerging. And something I did not talk about here, but it's one of the design patterns is actually having the multi-agentic systems, so agents can collaborate between each other, because as I mentioned, it's really important to have specialized agents instead of just one agent that does everything. And once you have these specialized agents and you want to use them for a specific outcome, they have to communicate and collaborate with each other. And for you, try and work on developing your model intuition, meaning like which models are good for which use case, which models to pick, when, how. And there is no better way than just experimenting, which takes me to the second step, which is like quick and dirty. Sometimes we keep, we take like weeks learning the theory, hypothesizing about like what might work, what may not work. But you will never know unless you get your hands dirty. So if I'm giving you any advice is, okay, learn 1, 2, 3 basics, foundations, start building on top of that, and learn as you practice. Because if you just don't start doing it, you don't know what will fail. You don't know what will happen. You just keep making these hypotheses that may or not be true. So the best way is definitely to go and experiment, and always have this mindset of evaluation. So evaluation needs to always be at the back of your brain whenever you're building your systems. And it's not just last minute thing. If you can do evaluation as you go, that's even better. So yeah, I'm the end of my presentation, and I hope it was helpful, and I'm happy to take any questions.
Yes, thank you very much, Nariman, for your information, for your presentation. It was a very insightful subject, and it is, I think, this is the most hot topic right now about LLMs and reasoning models. Also, I think that the presentation was very valuable in terms of drawing a very distinctive line between what an LLM is, what is its limitations, about reasoning models, agentic systems, and their limitations. Now I'm going to go ahead and ask you some questions from the comments. So there's a question here that says, does multi-agent systems generally outperform LLM-based single agents?
Yes. So going back to what I said a couple of times, that depends on how complex your system is, but having specialized agents definitely gives better output. So instead of having a single agent that does a million things, it cannot be good at all of those things. You want to have specialized agents, making sure that those agents do their specialized task well, and then combine them into like a multi-agent system.
Yes, definitely. Another question, it says, in general, LLMs suffer from hallucinations, given that even a single mistake in a chain of thoughts can lead to incorrect outcomes. How can real-world deployed systems reliably use LLMs as their backbone?
Okay. Um, so one way I said is that we need to go back and see the traces of our agents, like how our agent is thinking. It's like we're taking a look inside the brain of our agent. Um, and then once we see, for instance, that it is hallucinating, this is even before agents. So the way usually we deal with hallucinations is that we can fine tune our model, like on a specific, if we're working on a specific domain, that will help it not hallucinate on that domain, but we may be risking like some catastrophic for getting more general knowledge. So here it goes back to what your agent is, what is it specialized in. So maybe you want to fine tune it in that. Another approach would be to augment it with a RAG systems, because a RAG system keeps the agent grounded with factual information and more relevant knowledge. So if it has that context, it's less likely to hallucinate.
Yes. Yes, another question from my part. So, for tasks that are too sensitive for fully autonomous agents, but so complex for a rule-based workflow, as you have said earlier, what is the best practical way to combine both methods into a safe hybrid system?
Maybe if you can explain what do you mean by too sensitive for fully autonomous agent?
For example, in the medical field, especially, we have tasks we cannot let like an agentic system do the full for example, a surgery on its own. So it's too sensitive to let the agent fully handle it.
Okay. So what I would say is that these agents, models, agents, whatever, is here to help humans. It's here to, like, it's not here to replace a human being. It's not here to do the job for them, but rather it's like, it's the same way we augment the agent with tools, we augment humans with agents. Like they're here to help you. So if there is something that can be automated, can be done with this agent, and you can rely on it, of course, with some human intervention, like you're not gonna be completely let it do everything by itself. Then those are delegated to the agent. And then for more sensitive things, you build where everything is manual, and if you do it yourself, or like can be by some basic rules or like coding. So I think you, as the builder of the system, you are architecting what should be done by the agent and what should be done by you, because you know your system better.
Yes, definitely. Another question, it might be the last question. given the hardware and energy limits we are hitting with the compute power, how much further do you think current reasoning models and agents can really scale? Do you think that they will solve our biggest problems, or do you think that inevitably and eventually we will shift towards another paradigm like Jan LeCun's world models? What do you think about this?
So for my own personal view on this is that these agents or these models are not gonna like hit a wall and they can stop growing, like evolving. If compute is the limit, which I don't think is, so compute, I don't think compute is a limit, because we have been advancements both on the compute and the model side. So for the compute, we're building more capable GPUs, more efficient GPUs that consume less power, that have faster computations. And we also, for the LLM side, we're working on techniques to make these models smaller and more efficient. We have like quantization, distillation techniques. We using even like MVFP4 precision, going from floating point 16. So we're always making we're always making these new innovations, not only on the LLM and or the reasoning capabilities of it, but also on the infrastructure and the different way it can be deployed and used.
Yes, I understand. So yes, this is a very sensitive topic. I just wanted to know your opinion about it, especially that you work at NVIDIA, so you might know better what is going on in the hardware world. Yes, so thank you very much for your insights. And since this is the end of the session, and this is also the end of the season in School of AI Summit is actually the last event this year. And I hope that it was a success for me personally. It was a very successful event. We have learned a lot, and I hope that the impact of School of AI have reached a lot of people. Now, can you, as an ex co-leader of School of AI, leave a word for the School of AI community?
Sorry, say that again. Can I?
Yes, can you leave a word for School of AI community?
Sure. Well, before that, I just wanted to say that I'm delighted for the invite and for having me in this summit. It's a pleasure, and also to see what all my previous presenters did. It's amazing, and what all of you are doing, which is amazing. And for the word, I would say, well, it will not be a word, it will be more of a sentence or two sentences. So I would say never stop learning and never be intimidated. Even if you think you don't know something, there is no better way to learn than to admit that you don't know, try and fail. That's how you learn, and that's how it sticks with you. So just keep learning and don't be afraid to fail. If you are to fail, just fail fast. It's like the faster you fail, the better it is.
Thank you very much for your presence today. It was truly a pleasure to have you with us. And also your presentation was very insightful. I hope that you continue to contribute to School of AI community again. So
of course,
thank you, Narimane,
always will.
Today.
Thank you so much for having me. I appreciate that. Thank you.
The pleasure is ours. Thank you.